Hey, John here. Let's talk about bitwise operators, okay? What are the bitwise operators? Well, they look like these things, right? The tilde, the single ampersand, the pipe, the caret, that's XOR, right? Double left is a shift left, and a double right is a shift right. Now, don't confuse these with the insertion and the extraction operators when you're dealing with C in and C out and stuff like that, okay? C in and C out are more of the exception to the rule that overload these operators, okay? So if these are applied to an integer variable, what you're really doing is shifting it left, and this one here will shift it to the right. So let's look at some of these examples. Before we go into that, though, here, look, let's make sure that everybody's on the same footing. These are in stark contrast to these operators here, right? What are those things? You should have seen all these by now. If you write an if expression like this, you might say A and B like this. What we're really doing here is we're treating A and B, regardless of what they are, whether they're integers or anything else. This has to be a Boolean value in order for this operator to be applied to it. And this over here has to be a Boolean value, right? So if it turns out that A and B are, let's say, both integers, right? So you end up with something like 27 ended with, 0. What this would do is when the compiler runs, it would insert the code to change this integer into a Boolean, right? And that would change it to if, open parenthesis, 1, ended with 0 like this. Otherwise, it can't be done, right? This has to be converted from an integer to a Boolean in this particular example. If it's already a Boolean, it doesn't matter, and it'll just use the Boolean values. But these operators here deal with Boolean operands, is my point. The double pipe and the double ampersand and the bang, this thing is a not, right? For Boolean variables. If you might say if, not, A, and B. Oops. And you might recognize this. You got to put the parentheses in here because the not has higher precedence than the and. This right here in C or C++ is a NAND function. That's the NAND right there. A and B, and this is essentially put a bar over the top of it. Okay, we don't have graphical stuff in the C language, so you express it like this. All right, so these are logical. All right, let me just put logical up here so everybody knows. All right, homemade slip shot slide there. Those are the logical operators in C++. These other ones, I'm deleting all that you saw before. These are the bitwise operators. Okay, there we go. How do these things work? In many ways, they're very similar, okay? But these operate on all the bits of any given integer variable. These are all applied to integers, not Boolean values, okay? Now, the tilde is the not, okay? The single ampersand is the and. The single pipe is a or, XOR, and we already talked about that in the shift, okay? So let me get out of this thing. Program 1.cc. Let's take a look at this little program. If I could type. There we go. What does this thing do? We include the usual stuff. Using some stuff. What am I doing? I got a dump routine that prints out a signed and an unsigned value like this. And what are we going to do? We're going to set them all to 0 and dump them. Set them all to 1 and dump them just to get our bearings so we know what we're looking at. Then we're going to use this tilde operator. I'm going to say, well, I'll set my variable here to tilde hexadecimal 1. Okay, well, what does that mean? Bitwise not, you'll see that means this. That's one of these in hex, right? And in binary, what is that? I probably should have done this with less than 32 bits, but here, it's easy in Vi because you can go like this, and then I can say, do that 31 more times. Okay, so that should be 32 ones, 31 ones followed by a 0. This is why we don't use binary, by the way. You want to count all that out? No, I don't. Even this is annoying, but it's doable, okay? This is even easier, right? If you really want all these bits to do this, You know, there's your first F, 4 ones, here's the second F, and so on. It eventually ends with 1, 1, 1, and a 0. That's the E that you're going to see printed here, okay? Which is the exact bit for bit opposite, and that's the point of the tilde, of this thing. I only said, 8 bits worth here. I could have done this. All right? It still would work. In fact, let's leave it that way and see. Here's another one I could have done. 1, 2, 3, 4, 5, 6, 7 zeros and a 1. This one fully specifies all the bits of a 32-bit value. This might be a little more intuitive in your program to put it all in there, but both of these really mean the same thing. I'm assigning this to a signed 32-bit value, this one to an unsigned 32-bit value, okay? Let's go ahead and run this and take a look and see what that is doing at that point before we move on. So I run this program, I set them all to 0 and print it out. I set them all to the value 1 and print it out. Okay, that's brain dead simple. I then set both of them to this tilde hex 1. Well, that's the opposite of this, bit for bit. All zeros followed by a single 1 bit is all 1 bits followed by a single 0 bit. Again, this E right here is 1, 1, 1, 0. You don't believe me? Go look it up, count it out, create a truth table or your own binary cheat sheet that counts up to F with 4-bit numbers. That's what you're going to get. And it doesn't matter whether it's a signed value or an unsigned value. Tilde 1 is all ones followed by the 0. Okay? In decimal, because the dump routine also prints out the same value in decimal as it does in hex, you get these values. Well, if this is a signed 32-bit number, the value would be -2. The exact same bits, if it was unsigned, is this value. All right? This is why we don't use decimal hardly at all when we're dealing with anything low level in a computer. This number is pretty worthless. Do you know for a fact which bits are ones and which bits are zeros by just looking at this thing? I sure don't. But I do if I look at this. It's obvious. All these F represents 4 ones each, and this is your 3 ones and a 0. What's that? God knows. The only thing I can do off the top of my head is note that number is even, and therefore I know the least significant bit in there, it must be a 0. Okay? That's all there is to that one. All right, so let's go back and look at the next guy. So there's this tilde. What does it do? It flips all the bits in whatever this is. I can put, these are all just constants. I could just as easily said, some int variable, x equals hex 1, and I could have then come over here and said s32 equals tilde x, and I might as well do that. You int, oops, it's a signed integer, right? Int 32 t x equals hex 1. I don't even need to do it in hex, right? Because a hex 1 and a decimal 1 are the same thing. And I can just put this x in here. In fact, that's a bad variable because I got the x's and all over the place. Let's call this a for more readability here, okay? Same thing. I assign a variable to a binary 1 that's all zeros with a 1 at the end, and tilde a is the same thing. The beauty of a context-free grammar in the C language, you can use any function, any operation, anywhere where you need a numeric value. You can do the same thing, okay? So you see it didn't change anything. Just so you realize that the syntax, how I did this, was just to make it easy so we don't have all these extra variables, okay? But obviously it works either way. Let's look at the shift operator. I have a signed value and I have an unsigned value. What am I doing here? When you do things like, x plus equals 5, and what does that thing do? That will add 5 to x, right? Okay. Well, there's nothing wrong with using things like, you could even use and in here, and the or, as we'll see in a minute. So you can put double right arrow in there, okay? This would be the same thing as like the above thingy here. If I have this a variable, we might as well do it again. We already have a. It's defined up here, so we'll go ahead and say a equals the S32 is still set from up here to this value tilde a, right? So hey, It's already done. I can say equals a double right 1. In fact, I need to put the tilde in there. All right, so what have I done here? I suggest it's the same thing as I'm doing down here. A is the value 1. Okay? So tilde A is this value here. And then I'm shifting that right once. So what will that thing do? All right? These notes are backwards. That's not a logical shift. It's an arithmetic shift. Sorry about that. Way to stumble myself up in the middle of a dialogue here, okay? So yeah, my point is you can use shift right equals to say take the value currently in this variable and shift it right once, okay? Or you can say some variable equals something shifted with something else. If you do this, by the way, you need to make sure that the operator precedence is doing what you think it does. So we would ask the question, does it shift A right 1 and then do the tilde? Or does it do the tilde and then shift it right once? Okay? Well, to find that out, you do a lookup on Google. If you don't know, I happen to know that tilde has higher precedence, so it makes sense. It's like the minus sign when you're doing regular math. Google for operator precedence in C, and then go find one of these pages, and they got a chart in here. So it says, for example, the tilde is here, and you can see the bitwise left and right shift are down here. Therefore, we know it will do the tilde A, then it will do the shift, okay? So I'm throwing a lot out here at once. Pause it and go back and read all this stuff if you have to. So what's going on here? We take a signed value, and if we shift it right, I happen to know it's going to use an arithmetic shift because we're using the GNU compiler. And this, by the way, is not 100% normal, but it is normally how this is what most systems do, all right? It turns out how shift functions work is not formally specified in C. Whether they're always arithmetic or they're always logical depends on your compiler. By and far, though, most of them work exactly as I'm showing you right here. If this is a signed number, it'll use an arithmetic shift, which means it'll preserve the sign when it shifts right. If it is an unsigned number, it will use a logical shift, which means zeros will be shifted in as it goes. All right, so let's go ahead and compile this and run it before I get everybody too confused. So here's the part we were looking at, the not portable, but this is the norm. Okay, so what happens here? What did we do? We shifted both. These had the same value and they shifted right once. No matter how you slice it, we started out with this thing up here. Okay? In the case of the unsigned number, I simply just didn't modify the variable. In the case of the signed, as you saw, I restarted with tilde A and shifted it right once. But it's the same thing in both cases. So in the arithmetic shift, you'll see FFFFFF. It moved it to the right one, and it replicated the sign bit, because an F is all 4 bits. It's 4 bits all ones. In this case, that higher order bit changed to a 0. You can also see these E's became F's. Why? Because an E is 3 ones followed by a 0, and if we shift it right once, that the least significant bit that used to be a 0 is thrown away in order to make room for all the stuff moving to the right by one place, okay? So this is how you move things left and right. You can also shift the other way. So what do we got going on here? So there's the big mess that we just did. And we start off with a clean slate. So I'm going to say it's not quite a clean slate. Let me go ahead and comment this out in case it confused anybody. I'll put it back the way it was. S32 double right equals 1. This is the same thing. Okay, let me go ahead and throw that comment out. Because that's what it was up here, right? We don't need to start all over again. So what is it going to do? You just saw that the signed 32-bit value, after I shifted it right, was all Fs, right? All bits were 1s. This one was 7 FFFFFF, okay? A 0 bit followed by all 1s, all right? Now if I shift left 16, these are both going to be logical shifts because it doesn't matter whether it's signed or not. When you go to the left, they're all going to be done the same way. So we're going to go left 16, then we're going to go after that, we're going to go left another 15. So again, we're not resetting the variables. They retain their value from the previous one of these stanzas of tests, okay? So whatever the value is after the non-portable message is going to be then shifted left 16 and then another 15, okay? Let's recompile it. There's our not the norm, and you can see at that point when this part is done, all the bits are set in that variable here, 0 followed by all ones here, just like we just saw before. If you then take each of these values and shift them left 16, whether it's signed or not, 16 zeros are going to come in on the right, and we're going to throw away whatever was on the left. Again, these decimal values are kind of difficult to see what's going on. I would have never guessed that that is FFFF0000, or in binary, 16 ones followed by 16 zeros. It's not obvious to me. This is, again, worthless. This is useful if you want to know which bits are on and which ones are off, of course. If I shift it then an additional 15 to the left, and this all makes sense, right? 32-bit number. If I move it left 16, then I move it another 15, then all the bits must be 0 except for the most significant bit. And that most significant bit may or may not be on. In this case, they're both on because the least significant bit in this particular nibble or hit or hex digit, however you want to say it, bit number 16 right here is on. So when you move this thing left another 15, the bit that was in here is now way over on the left. It becomes essentially the signed bit in this case with a signed number, and it is the most significant bit of the unsigned number here. Okay? And if I move it left one more time, any bit that remains up here has to be thrown away. Okay? Now, the only reason all these bits are on here is because I started with so many on. Right? It doesn't matter. It doesn't mean that you're going to shift something and you're going to get a 1 over here. No, it means whatever used to be over here is going to be moved to the left. All right? I mean, the F doesn't become an 8 because I shifted it. This F here becomes an 8 because I shifted it 15 times and threw away so many bits that only one bit of these 16 are still able to be left in this number, and it just so happens that I chose a value that's 1. And I did that on purpose so it's easy to see where they ended up, okay? So this is how you can shift things to the left and to the right. So now what do we got? What other operators did we have in the list of operators we were looking at? We just looked at the tilde, and we looked at shifting left and right. So what do we got here now? We got a little dump routine. What does it take? It dumps a little message out. Then it takes a 32-bit unsigned value. So it's going to print the little message that I give it, followed by equals 0x, and then the hex 8 bits, and then the decimal in parentheses like we saw before. Okay. Let's look at this little program. What does it do? I got 3 unsigned 32-bit values. Now, everything you're looking at here will work with 16 bits, 32 bits. It works with signed values, unsigned values. Why? Because the system doesn't really care what the data type is, as long as it is of an integer type. All this math, all the operations that you see will work. Again, we're dealing with bitwise operations. These are all going to be AND operations, okay? Now, unlike the Boolean ones, the bitwise operations, you saw how the shift worked. We're moving these bits to the left and the right. Well, the AND operation, what it's going to do is it's going to take this as a binary value, and each of these 32 bits independently, when I do this, I'm going to AND A with B. Okay? That means the least significant 2 bits right here that are in here and in here will be ANDed together without any regard to anything else in there. And we can see clearly the least significant bit here is on, and the least significant bit here will be on. Okay? what's the next bit? So that would be like bit 0 is the least significant bit. Bit 1 in here is a 0. Okay, bit 1 in here is a 1. All 4 of the bits in here are 1s, right? This is 0001 in this hex digit here. So what happens when I AND those 4 bits with these 4 bits down here, I'm going to get 0001. Okay, and when I get all these guys here ANDed with all of these here, they're all going to be zeros, because each of these remaining 28 bits that are all 1s will be ANDed independently with all the bits in here that'll be all zeros, and anything ANDed with 0 is 0. So when you AND A and B together, you should get 1. When you AND A and C together here, you should get a 0. All right, so let's look and see what happens in there before we move on. Prog 2, let me clear up my screen a little bit. Okay. What happens here? There's my 1, there's my all 1s. My C was set to 0, so I said, what's A ANDed with B? And just like I said, it's 1. Because each individual bit hiding in these 32 bits are ANDed together. And this thing here ANDed with all zeros is 0. If you don't believe me, again, grab a piece of paper and a pencil and draw this out in binary and long form and do them all that way. It's difficult for me to see these things. It turns out that I could do this particular one in my head. I chose an example that I can do. This number here is odd, and this number here is simply 1. Therefore, I know they both have the least significant bit set, and because this is 1, this one's obvious. There's only 1 bit set in here. I don't know what bits are in here on the top of my head. I can see it clearly here, but this one, they're both odd, so I do know the least significant bit will be set if I AND this in decimal with that in decimal. Okay? And because that's the only bit set here, I know that would be the answer, even in decimal with this hideousness. But if you look at these down here, no way. Beats me. I'd be here a week converting this stupid thing into hex, and then I could do it, right? And it would take a long time. So working in hex when we're dealing with these bitwise operators is definitely the way to go. All right, I can't emphasize that enough. So what do we got here? We're ANDing some more stuff together. We don't need to look at the source code. These comments should show you what's going on. I set A to this, B to that, and C to this, and then I AND them together. And look what happened here. If I have 16 1s down here in the least significant half of this 32-bit variable, and I got 16 zeros over here, and I just have a bunch of stuff up here, well, for every 1 bit here ANDed with, some value, that value will just propagate into the result as is, okay? All the zeros in here will be annihilated. Go back and look at the Boolean algebra functions, right? The annihilator for AND is a 0. Anything ANDed with 0 ends up being 0. So that's why you got zeros over here, okay? And what happens down here? I AND A with C. Well, this time, I just put all the F's here. All the 1s are moved into the middle. And these are easy because I'm doing something with F's. These are the easy ones because you can do them in hex directly as you're seeing them. If it's anything ANDed with F is the thing. So I got 0 ANDed with 1 is 0, 0 ANDed with a 2 is 0, and that's why these 2 zeros are down here. I got 3, 4, 5, 6 ANDed with F in hex gives me the 3, 4, 5, 6. And I got 7 and 8 in hex ANDed with double zeros over here, and that's why those are zeros, okay? Again, no way would I know that that decimal value equals this thing here. I couldn't tell you that the most significant 2 hex digits are zeros by just looking at this thing. It would be difficult for me to do, okay? Work in hex. What's this one doing? Now we're going to get more creative. Again, they're still easy because these are always with F's like this, all right? So I can do these in my head pretty simple. What do we got here? I got another situation where I got a bunch of values and I just got this. I didn't change that one at all. That's the same as up here, 1 through 8 and all 4 zeros and 4 F's. So if I AND A with B, I'm still going to get the same thing, 5, 6, 7, 8. But the interesting thing here is this, okay? Now I spread them out a little bit. What am I doing now? I'm letting every other hex digit go through this AND function. 4 bits here ANDed with all zeros here. No matter what that is, I'm going to get zeros. some value, call it Q, 4 bits, ANDed with 4 bits of ones is going to give me whatever the value is, Q, right? Something ANDed with all zeros is going to give me all zeros again, and so on. So this is OF, 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 gives me 02, 04, 06, 08. So what did I do? I shut off every other one of these digits. And these are generally called AND masks when you're doing stuff like this. You say I've masked off these bits. All right? What happens down here? This one's harder. Okay? So I got a 1, 2, 3, 4, 5, 6, 7, 8 in hex stored in the A variable. And I'm going to AND it with all C's. Well, remember that a C in binary is 1100. So if I AND 0001 with a 1100, I should get 0. Okay? What's this thing? That's one. The hexadecimal 2 is a 0010. And it with a 1100. So there's no ones that align with any ones up here, right? So I'm going to get another 0. Same thing with 3. That's 0011. And I'm ANDing it with a 1100, and I get a 0. Now it gets interesting. What is 4 ANDed with C? If you can't do it in your head, get out a piece of paper. 4 is a 0100. And I'm ANDing it with a 1100. So I end up with the 4. Okay? Oh, what's a 5? In binary, it's a 0101. See? 1100. Therefore, what I did is I kept the 2 upper bits of the 5, and I threw away the lower ones, and I ended up with a 4. What's a 6? 0110. ANDed with 1100. I threw away the lower one again, and I end up with a 4. Well, what's a 7, right? 0111. Well, this thing shuts off both of those 2 least significant bits hiding in that 7, and I end up with another 4. And an 8 is 10, followed by 00, ANDed with 1100, and I get the 8, okay? So this time I masked out bits in pairs. Again, work it out on paper if you can't see it in your head. What's this one going to do? What do I got here? I got 8 bits that are on here, followed by 24 bits that are off here. And I shifted it right 1. So what do I get here? I got FF, and now here I got 07F8, What have I done here? I got 8 bits on here. I'm having a hard time highlighting that. I still have the 8 bits in here all set, but they're not lined up cleanly anymore with the hex digits. What do I got? I got a 0, 1, 1, 1, 1, 1, 1, 1, and then I got a 1, 0, 0, 0. 8 bits on here, 24 bits off. I still have 8 bits on here, but I moved it to the right one. There's 23 bits off over here and 1 bit off on the far left. Okay? What does this remind you of? Those are the 8 bits positions that coincide with our floating point thing here, right? That's this right here. There's 8 bits that represent this exponent in a floating point number, with 1 bit on the left for the sign and 23 bits over here that represent the significand, okay? So what I've just done here is I've created a mask that down here you can see me use. If I AND this thing with this thing, and if this thing up here happens to be the hexadecimal value of this IEEE floating point number, what I've done is I've extracted the exponent out of it. It's hiding in here. But it's way over in the left, okay? It's these guys here. What have I done? With the AND mask, I've shut this off, and I've shut all these off. I forced all those to be zeros. But I've retained whatever the settings are of these bits here. That's what I did when I ANDed it with this thing here. So if that's an IEEE floating point value, I've extracted the exponent. If I then take this value here and shift it right 23 bits, I will have moved the exponent bits from over there over to the right. And look what I got in decimal now. This value here, 0 or hex C0280000, is the example you're looking at right here. Look what this is. 4 bits right there. That's a C. 1, 2, 3, 4. That's a 0. 1, 2, 3, 4. That's a 2. That's an 8, and the rest are zeros. So that's a C0, whatever it came out over here. C0, yeah, C0280000. It turns out in floating point is this negative 2.625. If that is a floating point number, all right? So if you ever have to extract the exponent and understand what it is, or even print its value out, you need to do things like that. That's why you need to be able to and mask. We need to be able to shift and stuff like that. So what does this one do? Here's another example of some value, and I did the same thing to it. Let's just assume it's another one of these floating point values. Again, I'm going to AND it with this thing, and I'm going to shift it right 23 positions. If you started with this, you can clearly see because of all those F's that that exponent has all of its ones on. Okay, so it makes sense that once it's been extracted and it's an 8-bit value, that it would be this FF here, which is 255. Okay, so this is one of the applications you can do with and the shifts. Okay. Now, once you've seen how AND works, things like OR and XOR are going to be the same thing. So I went through here, I have the exact same values, and I ran the exact same examples, but I put OR in there instead I did the AND. I did not do the shifting combination with the OR. I only did that last one because it matches how you would extract that exponent. You would never do it with an OR, right? Because if you ever OR something with 1 bits, you end up with 1. Instead of, the other way around. So what do you do with an AND? You use it to figure out which bits were set, and you force all the extra ones off. That's kind of what you're doing when you use AND masks. If you're going to do an OR, what you're really doing is you're saying, let's say I'm going to OR A with B here. I'm just saying, force all these bits that are given here to become 1s. So if I say OR A with B down here, I got A is set to just all 0s and a 1, and B is all 1s. If I OR that together, clearly I'm going to get all 1s, right? And down here, if I OR A with C, I got all 0s followed by a 1, ORed with all 0s. Well, then I'm not adding any more 1s by ORing them in, right? I'm going to end up with a 1 when we see this thing run, all right? And for some reason, I didn't, I see. I didn't see fit to put a heading on here because what I'm doing is I'm printing out the variables and I'm printing out the operation on the left. So let's just go ahead and run this and just have an eyeball at what's going on. Again, these decimal values are kind of worthless. The hex ones are most useful, or even binary. But again, I can't, personally, I find it annoying to see 32 bits in a row on the screen. So what happens when I got A ORed with B? 1 ORed with all 1s is all 1s. 1 ORed with all 0s is just the 1, right? I got a 1, 2, 3, 4, 5, 6, 7, 8 ORed with all 0s followed by 16 1s. And what do I end up with? Well, all the values that are ORed with 0 are left alone. All the values that are ORed with 1s become 1s. So I end up down here. What I've done here is literally the opposite of when I use the AND mask. When you use an OR mask, you're forcing them all to become 1s. The AND mask would have forced all these to become 0s, okay? And again, here's the one where I've got some in the middle. It doesn't matter which ones you want OR to turn on and which ones you're going to turn off. And again, you see the FO, FO, FO. And when I OR A with C right here, you can see 1F, 3F, 5F, 7F. When we did this with the AND, what we ended up with is 0, 2, 0, 3, right? Because the zeros forced off all those bits due to the logic of the AND, okay? What do we got down here? 1, 2, 3, 4, 5, 6, 7, 8, ORed with all C's, okay? Again, all of them up here are real easy to do in your head, I would argue, because F's and zeros are great because they all line up in hex. You can just do it in hex directly. If you got this, you have to think in binary. And a C is a 1, 1 followed by a 0, 0. So if I OR a C with a 1, I'm going to get a D, right? Because C is 1, 1, 0, 0. And that's a 0, 0, 0, 1. And you're going to OR them together on a per column basis. So the least significant bit of this hit is 1, and it's ORed with a 0 in here, which becomes a 1, right? And the second bit in each one of these is a 0. And the third and fourth bit in here are 1s. The third and fourth bit on the left are 0s. So you combine all that and you end up with D. Okay? 2 ORed with C, it becomes E. 3 ORed with C becomes F. All right, and inside your head you can sort of see that, I hope. 3 is 0, 0, 1. And this is 1, 1, 0. You OR all that together and you get all 1s, right? In here, that's a 0, 1, 0, 0, is it not? And that's a 1, 1, 0, 0. So the 4 doesn't, it's redundant. It doesn't contribute much. That's why we still end up with a C in here, okay? The 5 is 4 plus 1. You can see that in your head. Therefore, this is a 0, 1, 0, 1 in binary, ORed with a 1, 1, 0, 0, and you end up with 1, 1, 0, 1, which is a D. So again, grab a piece of paper and a pencil and work these things out if you have to. Okay? You're going to really need to have in your head a halfway decent way to remember how the hex and binary stuff works. Or otherwise, you'll be kind of slow when you're working on all this stuff. You'll get the hang of it as you go, I'm sure. Let's look at the next one. Should be XOR. Our friend, the exclusive OR. Remember, this is the the parity function, or if they're both the same, you get 0, and if they're both different, you get a 1. Now, the XOR is only a binary operator in C. You cannot have an XOR function with 3 operands. Okay, and this is why a lot of people just simply say that it's true when they are different, and it's 0 or false when they're the same. Because most languages that implement this in software, the exclusive OR operator only has 2 operands, okay? But if you're building hardware, you can build a gate that can do it in hardware with as many inputs as you want. Therefore, you really want to keep in mind that how this thing works. Okay, so what do we got here? Again, I got all the same values we've been seeing the whole time. I'm going to print them out, and I'm going to just do them. A XOR B, A XOR C. Again, these are bitwise. On a per column basis, we're going to apply that Boolean function. Make this, if it's not made already, prog 4. What happens this time? We got a 1 XORed with all 1s, right? So there's a single bit that's on here, and all the bits are on here. You XOR each one of these columns, one at a time in your head, all 32 that are hiding in there, okay? Well, this has a single bit on, and this has all of them. Therefore, the least significant bit is on in both, and if you use the same difference rule, or even an odd parity, parity is even, and they're the same. Therefore, the least significant bit, if you XOR A with B, like I do right here, better be a 0. And you can see that it is, because the hex E value is 1110. And all 1s here, XORed with all 0s here, are all 1s in the result. Okay? If we take this and we XOR it with all 0s, 0 XORed with 0 is 0 all the way down the line. And 1 XORed with 0 is 1. That's why this thing down here is still 1. So if you ever take anything, call this A, XORed with all 0s, you're going to get A. If you ever take something A and you XOR it with all 1s, it's the same thing as getting a tilde A, is it not? What I've done is I've flipped all the bits in this A variable by simply XORing it with all 1s. So quite often you use the XOR this way, as you'll see down here, to reach into a variable and say, look, I want to leave these alone, but I want to flip these 16 bits, whatever they are, invert them. So what are you going to do? You're going to XOR it with a thing that looks like that. So what happens? All these 0s XORed with whatever is still whatever down here. A XOR B. So the 0s here result in no changes. But look what happened here. A987. How does that work? Let's start with this one down. Let's work from the least significant bits to the left. It's easier for me to do an 8 in my head, because an 8 in hex is a 1 with 4 zeros after it. And I'm going to XOR that with all 1s. So what's that going to do? It's going to flip all those bits. 8 is 1 followed by triple zeros, and it's going to give me instead a 0 followed by triple 1s. And that's what a 7 is in hex, is it not? Okay. Now I got a 7 XORed with all 1s. Well, just like 8 inverted is 7, 7 there logically inverted is an 8, okay? 6 inverted is a 9 because a 6 is 0, 1, 1, 0. XORed with all 1s becomes 1, 0, 0, 1, which is a 9. A 5 is a 0, 1, 0, 1. XORed with 1, 1, 1, 1 gives you an A because that's 1, 0, 1, 0. Okay? So where the AND function says zero out a bunch of stuff and then pass through a bunch of stuff, and the OR says pass through a bunch of stuff and set a bunch of stuff to all 1s, the XOR says pass through a bunch of stuff and then flip all the other bits that have 1s. Okay? And whatever bits you're XORing with becomes the one that are flipped. So if I move this to the left a little bit, I take this value, shift it left 8 bits, I get this thing. And you'll notice that where the zeros are here, the 1 and the 2 still propagate fine. Now these guys here, these 4 values here are binary inversions of these up here. And these 2 zeros XORed with the 7 and the 8 do nothing to it, and you end up with this, okay? And then we do the same thing with the OF, OF, OF that we saw before. Again, the zeros line up with the values that are passed through as they are. And these hexadecimal Fs, XORed with like 6 and with 8, it will do the same thing they did up here, okay? Now we get to the tricky one down here. Again, grab a pencil, work it out. Remember, this is all working in binary, 1 column at a time. 8 is a 1 followed by 3 zeros, and you're going to XOR that with a 1, 1, 0, 0, which is what the C is. And that means we're going to invert the left 2 bits of this value. So instead of 1, 1, 0, 0, we'll end up with 0, 1, 0, 0. That's a 4, okay? You don't see this, you can't work this in your head, grab a pencil, paper, work it out. If it's not intuitively obvious, you go ahead and send me an email if I'm totally out in left field here. But that's what's going on in here, all right? So that's what the bitwise operators, we call them bitwise, because each bit hiding in these hex digits or these hits are operating on their own in that one column. There's no carries, there's no borrows, all right? Now, the shifting, of course, is going to affect its neighboring bits because you're going to move things to the left and right, okay? But the AND, OR, the NOT, and the XOR is just going to happen on a per-bit basis, all right? So that's all there is of the binary operators in C and C++. Thanks for watching. Have fun. Be safe. See you next time.